So we've been talking about one-dimensional motion where objects move at a constant velocity, whether positive or negative. So no acceleration and zero slope velocity versus time graphs. Today we start talking about Newton's laws and about how forces can cause a change in velocity, can cause an object to speed up or slow down. And we started with the tablecloth and dishes and the idea of inertia, Newton's first law. So, Newton's first law states that an object likes to maintain whatever motion it has. And like these dishes here, they are at rest, they have a velocity of zero, and they don't want to change that. It requires a force to get them to move. And if I can pull the tablecloth out fast enough, overcome friction, then there's no force to actually accelerate the dishes, so they stay right there. Okay, and we talked a little bit about ancient thoughts of motion, at least European thoughts on motion. Go a couple of millennia back to the Greeks, like Aristotle. The idea was that there is things like smoke rises, and it rises because it's going up to where it wants to be or where it naturally should be, which is up. You know now that smoke rises because when things are burning, they're hot, and hot things expand their volume, and so the smoke is less dense than the air around it, so it rises. But to them, smoke rises because it wants to. And planets circle the Earth because they want to. It's natural for planets or the gods, because Jupiter and Venus and Mars, these were gods. And they were up in the sky and they circled the Earth in these perfect orbits, and they themselves were perfect. And things like rocks falling or anything that you drop falls because it naturally wants to go down. So to the ancients in Greece, not in the rest of the world, but in the European area, these were all natural motions. Things falling, planets circling the Earth, smoke rising, they just want to. And the other type of motion was violent motion. And that was everything else. That it wouldn't move unless you pushed it or forced it or pulled it. You committed violence against it. And this sort of motion of planets circling the Earth, it resulted in a solar system map like this one here. If you'll notice, Earth is in the center, and all of these lines are the motions, the orbits of planets around the Earth. Okay, and they have these little kinks in them. And having a solar system map like this is necessary if you consider the Earth to be the center of the universe. Almost 2 millennia later, almost 2,000 years later, a Polish mathematician and astronomer named Copernicus, he was an astronomer, so he watched the sky. And he watched the sky. He didn't take photographs because he didn't have a camera, but he made drawings night after night of the motion of the planets. And here, the main one here in the middle is Mars. And it's kind of easy to think that the sun circles the Earth because it rises in the east, it sets in the west, it rises in the east again. It looks like the sun revolves around the Earth. And the moon also. The moon does revolve around the Earth, so it's easy to think that everything revolves around the Earth. But if you'll notice these pictures of Mars night after night, taken about the same time every night for a couple of months, shows the true motion of planets as seen from Earth. They kind of go in one direction and then they turn around and come back. That's true for Mars and Saturn and Jupiter and all these planets. They have this back and forth motion. They don't really, if you really pay attention, they don't look like they actually circle the Earth, which is why it led Copernicus to the idea that the sun must be at the center. If you'll notice here, the Earth is going a little faster than Mars. So this is Mars, this is the Earth. And Mars in our night sky does look like it's moving along, but then as the Earth catches up to it in our orbit, Mars switches directions as we pass it, and so does Jupiter, and so does Saturn here. That's what gives you that pattern of planets actually wandering back and forth in the sky. They were actually originally called the Wanderers. But Copernicus said that if you just put the sun at the center of the universe, of the solar system, then you don't need that crazy gyroscope drawings. You just need these circular orbits to explain the motion of the planets. Okay? But he never published this information. He was afraid of being put to death for speaking out against the leaders of, in Europe, the royals of the church. So he didn't publish it in his lifetime. He had his findings published after he was dead. And about a generation after Copernicus died, Galileo was born. And Galileo didn't invent the telescope, but he did improve on it. And he was a firm believer in Copernicus's idea that the sun was the center of our solar system. And this is a video of Jupiter, the sun off to the right, lighting up this side. And you can see these four called Galilean moons because Jupiter's four big moons were discovered by Galileo with his telescope. And you'll notice that they orbit Jupiter. And you also notice that they go into the shadow. So as they go around and they get over here, they actually blink out when they go into the shadow of Jupiter. So the sun's light doesn't shine up, then they come back in. But here, this was important because the idea that the Earth was the center of the solar system and that all the planets were perfect point of light gods up in the sky circling the Earth. When he got his telescope and looked at Jupiter, he could see that, the moons orbiting Jupiter were four items that were not orbiting the Earth. So if the doctrine is that everything orbits the Earth, here's an obvious visual. You can see for yourself that these things are not orbiting the Earth. They're orbiting Jupiter. So that's evidence against the Earth-centered system. He also noticed that the planets, and he made drawings of them night after night, and he noticed that they were spheres just like the Earth, and that they rotated, and they had imperfections in them. They had storms and clouds, and they weren't perfect little points of light. They weren't gods. They were planets, just like the Earth. So Jupiter here and Mars here are both just spinning globes like the Earth. So that's also a point where it can't be the Earth-centered, because with these perfect gods orbiting around them, because they're not perfect gods, they're just planets like the Earth is. He also watched the sun through a telescope, and he noted that the sun was also a sphere that rotated, and it had blemishes on it. It wasn't a perfect god. It was a big, bright ball in the sky that had little blemishes on it. He also noted that Venus had phases just like the moon, and you can see as the phases go along that Venus grows and grows and grows and appears to be a sphere, not a little point of light and a god, but just a sphere, a planet like any other planet. You also notice that the moon, if you look closely at it through a telescope, it's not perfect. If you look on the edge especially, you can see that there are ridges and mountains and valleys and craters. So the moon also is not a perfect godlike figure. So all of these things told Galileo that he believed Copernicus's idea that the sun was the center of the universe and that all the other planets are just planets, they're not gods. And then, here, Galileo died in 1642. On Christmas Day of 1642, Isaac Newton was born. And he was the one who finally proved that, mathematically proved that the sun was the center of the solar system. But he got there after doing a bunch of different things. Newton is the greatest scientist ever. He was the person who first worked with light and could break light up into its colors, the rainbow. And he noted that those colors were split refracted at different angles. So they didn't just come out, they weren't all the same, they were different frequencies, different bands of light. So red is different than yellow and is a different frequency than green or blue, and that they were energy. And he also noted that when you used a regular telescope with a lens like Galileo's, the lens tended to split the colors out. So if you were looking at Jupiter, the colors would be washed out of the planet and would end up as a rainbow ring around what you were looking at, the image in your telescope. So he developed the reflecting telescope, which means just mirrors, no lenses to refract the light. And his telescope, called a Newtonian Telescope, is the same type of telescope used today. The Hubble Space Telescope is a Newton telescope. All these big giant telescopes on top of mountains or in space are a Newton design telescope. They have computers and better detectors now, but they are his design, basically. Newton invented calculus to find the speed of things that are speeding up or slowing down, to find speeds and instantaneous speeds of objects that are speeding up or slowing down. So he worked on the integral and the derivative. He also is the one who proved that planets travel in ellipses. So Copernicus's model of planets traveling in circles didn't really work well to predict where the planets were, because planets don't travel in circles, they travel in ellipses. Sometimes they're closer to the sun, sometimes further away. They speed up when they get close to the sun and slow down when they get further away from the sun. Just like the Earth is closer to the sun in our summer, or in our winter, and further away in our summer. And all planets operate in ellipses. He discovered universal gravitation, that gravity is the same everywhere, and he came up with equations to quantify how fast something will move, how it will accelerate based on its mass and the force being used to pull on it, the gravity pulling on it. He worked out ideas of inertia, that objects like to maintain whatever motion they have. If they're at rest, they like to stay at rest. He came up with his equation for acceleration, which is acceleration is directly proportional to the force being applied and indirectly proportional to the mass of the object. And we'll deal with this in a couple of labs here in the next couple of days. All of these things make Newton the greatest, most productive scientist ever. He's literally once in every 5,000 year kind of person. Okay? And the little oddity about Newton is all of these things, he didn't tell anybody when he made all these discoveries. He kept them to himself. It wasn't until an astronomer came to ask him to mathematically prove that planets travel in ellipses, that his telescope was seen for the first time, and he became famous because of that little tiny reflector telescope he had made. And then everybody... after he published it, he became famous for calculus and gravity and all those kind of things. Okay, so Newton's first law of motion is that it takes a force to change an object's motion. Objects like to maintain their motion, even if that motion is zero. So this little kid in the cart there, he is requiring a force to move him, to speed him up and move him. He's requiring a push, a force.